All right, we're ready to go. So 5.2 mean value theorem. Okay, mean value theorem. So we're going to do the mean value theorem for derivatives. Okay, the mean value theorem for derivatives. Go to page 202. There is the theorem number 3, mean value theorem for derivatives. If y equals f of x is continuous at every point of the closed interval a and b, and differentiable at every point of its interior points, then there is at least one point c in that interior points at which the instantaneous rate of change equals the mean rate of change. Okay, so there's a lot of ifs here, okay? So first of all, the mean value theorem of derivatives, we also learned what was called the intermediate value theorem. We also learned what is called the intermediate value theorem for derivatives, okay? And now we're learning the mean value theorem of derivatives. So it's kind of a good time to think back on those, all right? Kind of make sure you get a grasp of these things, all right? So I would highly recommend that you go back and take a look at those. So in this one, the mean value theorem of derivatives, we are saying that if on this closed interval, f of x needs to be in this closed interval and needs to be continuous. And in the interior points, it needs to be differentiable. If that is true, what they're saying that somewhere in the interior points, somewhere there is going to exist an x equals c, where at that point, okay, the differentiation or the slope of the tangent line at that point is going to be equal to the average or mean rate of change there, okay? So the ifs are, it has to be continuous, and it also has to be differentiable, okay? If these are true, then there is a point, an interior point along between A and B where this holds true. Okay, so what does this actually mean? What this actually means is this. So let's go ahead and look at this graphically. If I drew a graph, and let's say that I had a function that looks like this, and we have point A, point B here, okay? The average rate of change, f of B minus f of A over B minus A, okay? The mean rate of change is nothing more than the slope between these 2 points, this point and this point, okay? Because this is A, f of A. The point here is the coordinates are A and f of A, right? So I'm gonna get A and f of A here. I'm gonna get B and f of B here. All right, so the rate of change, or is the rise over the run, f of B minus f of A over B minus A, right? Okay, so somewhere along in this, between A and B, there's going to be a place where the tangent line slope is the same as this. So where is that? It's going to be right up here, right? So it's going to be a parallel line because it's going to have the same slope, and it's going to look like that. Right, so because these two lines are going to be parallel, right? So there's going to be a point C somewhere here. There's going to be a point C where the slope of the tangent line, which is nothing more than f prime of C at that point, is going to be the same as the mean rate of change. And that's what that's saying. Okay? So graphically, this is what it means, and that is on figure 5.11, I guess, on the left-hand side of page 202. Okay? So let's see if we go ahead and explore a little bit on this. So let's see if we can use this. And let's see if we can go through some of the examples here. So example number 1. Exploring the mean value theorem. Show that the function f of x, x squared satisfies the hypothesis between 0 and 2. So I have y is equal to x squared. This is 0. We'll call this 2. The value at 2 is going to be equal to 4. So this is 0.2 and 4. This point is 0, 0, obviously, right? So the mean rate of change is 4 minus 0 over 2 minus 0, which is equal to 2. So somewhere between here and here, I'm going to have a point where the slope of the tangent line is going to be equal to 2. And that's what I'm going to try to find. Okay, and how am I going to find that? I'm going to find that by saying f prime of x is equal to the derivative of that, which is 2x. So somewhere this is going to be equal to 2. So that point is going to be x equal to 1. When x equals to 1, basically what I'm saying, what they're saying is that at x equal 1, I'm going to have a slope that's going to be equal to 2, equal to that. Okay? So that's what that means. So that's how that works. Let's go to example number 2, exploring the mean value theorem again. So in example number 2, we're getting a little bit into the nitty-gritty here. And let's see what we can find. Example number 2, explain why each of the following functions fails to satisfy the conditions of the mean value theorem between -1 and 1. So the first one is f of x is equal to the square root of x squared plus 1. Okay, which is basically what? This is the same as the absolute value of x plus 1, which means that the graph is going to look like this, right? 1 is the absolute value would start at the origin here, but I'm going to raise it up 1, right? That's all I'm doing. In between -1 and 1, okay, and if you look at it, the slope is going to be equal to 0, but the slope equals to 0 is going to be this point here. However, this point here, the f prime does not exist, right? Because it's a little pointy point there, right? There's a cusp right here, so it does not exist, right? In other words, which condition does it not meet here? The conditions are it has to be continuous between here and differential between here, right? So it is continuous here to here, right? Because I can draw it without lifting my pen. It is continuous. However, it has a point where the differentiation does not exist there, right? So that's why it fails. Okay, let's go and look at the next one. So that was A. Let's look at B. B, y is equal to x cubed plus 3 for when x is less than 1, and when x is greater than 1, it's x squared plus 1. So x cubed plus 3 is going to look like this, right? X cubed plus 3. And this is going to happen until when x is less than 1. So if this is 1, so it's going to happen from here, and that is going to be an open dot. And then I have x squared plus 1 when x is greater than x squared plus 1. So plus 1 go here, like that. So this is the graph. So obviously between -1 and 1, what's happening here? Between -1 and 1, we have the function has a discontinuity at 1, right? So it's not continuous. So basically, it is differentiable between here and here, right? It's differentiable between, in the interior points, it's differentiable. However, it is not continuous here, right? Because I have a discontinuity here at the end point. Okay, so that's where that one fails. Okay. All right, let's flip the page, go to example number 3. Example number 3, let f of x equals that. A and B, find a tangent line that is parallel to the secant AB. Okay, so y is equal to square root of 1 minus x squared, 1, negative 1, 1, right? It is the upper half of the circle, right? It's a semicircle that's on the upper half because y has to be greater than 0 here, right? Y has to be greater than or equal to 0, right? So this is going to be point A. This is going to be point B. Okay, so the question is, find a tangent to F in the interval that is parallel to the secant AB. The secant AB is nothing more than this line segment here, Okay, so I'm trying to find a F prime where it is the same as that. So it's obviously going to be up here, right? Because this is 0, a slope of 0, right? So it's going to be right here. Okay, so that's going to be right here. So obviously this is the point right here. So it's going to be f of prime is equal to 0 when x is equal to 0, right? Okay, that was pretty simple. Okay, let's go move on. It says the physical interpretation, So example number 4, it says interpreting the mean value theorem. If a car accelerating it from 0 takes 8 seconds to go 352 feet, its average velocity for the 8-second interval is going to be 352 divided by 44, or 44 feet per second, or close to 30 miles per hour. So what that mean value theorem is saying is that between that 0 and 8, that time when you're accelerating, there's going to be a certain point at which your gauge is going to actually say 30 miles per hour. Okay, and that's what that means. Okay, so, all right, increasing and decreasing functions. There's a green box, definitions there. Increasing function, decreasing function. Okay. F is increases on the interval x1 when less than x2 when f of x1 is less than f of x2. Well, that makes sense. That means it's increasing, right? So decreasing is the other way around, and that makes sense. So in other words, a function looks like this, x1, and this is x2. This is a decreasing function here because f of x1 is greater than f of x2. Okay, and you can notice here that the slope of the tangent line is going to be negative at this point. Okay, if I have a part where it's actually increasing, x3, we'll call this x4. F of x4 is going to be higher than or greater than f of x3. And as you can see, the slope is going to be positive when it's increasing. So in other words, when the function is increasing, the corollary to this is that your f prime is going to be greater than 0. So the corollary 1, if f prime is greater than 0 at each point of between a and b, then f is increasing during that interval. If f prime is less than 0 at that point, at each of those points between a and b, then it's the opposite. It's going to be decreasing. So you can tell whether a function is increasing and decreasing by looking at the f prime and see if it's greater than 0 or less than 0. Okay? All right, so let's go to example number 5 and see if we can use this and do something with it. Example number 5, determining where the graphs rise or fall. The function y is equal to x squared is, okay, so if we have y is equal to x squared, we call this f of x, then f prime of x is equal to 2x. So when x is greater than 0, it's increasing because this is positive when x is greater than 0. When x is less than 0, it is decreasing, right? Because when x is less than 0, this becomes a negative value, right? When you think about it, it makes sense because x squared looks like this. So when x is greater than 0, it's obviously increasing. When x is less than 0, it is decreasing because I have a negative slope right here, right? Okay. So that's that. And let's do one more. Let's do example number 6. And then I'll give you a break. Example number 6. Example number 6, since the function, where is this function increasing and where is it decreasing? So f of x is equal to x cubed minus 4x. So when is it increasing or decreasing? So f prime of x is equal to 3x squared minus 4. And when f prime of x is greater than 0, it's increasing. So it is increasing when this guy happens, which means that it is 3x squared over 4. I can divide both sides by 3 at this point. So when x squared is greater than that, so when x is greater than 2 root 3 or x is less than negative 2 root 3. This is when it's increasing. When it's decreasing is when this is less than 0, which means that 3x squared minus 4 has to be less than 0. 3x squared 4, divide both sides by 3, I get this. This is x squared, by the way. So then I have x is between 2 root 3 and negative 2 root 3. Okay? So this is when it'll be decreasing. This is when it'll be increasing. Okay? And if you graph that, you can verify that and make sure that is correct. Okay? So we'll stop right here. And I'll let you guys start working on the homework. We'll go from there.